Hani, along with Johanna and Christian, will be presenting to you our project titled the Novel Intrabody Communication System with Optimal Electrodes on a Flexible Substrate. Now, let me tell you, it's confirmed. Wearables are the next big thing according to CNBC News and the Time magazine. Wearable devices are being used for continuous, unobtrusive monitoring and tracking of many different biological markers, such as blood pressure, skin temperature, respiration rate, and muscle activity, for example. It is also projected that we will be using more than 2 billion wearable devices by the year 2030. Now, why should we monitor or track, you may ask? Well, for two main reasons. First, this will be life-saving with people with health issues. And number two, it can provide us with personalized training plans for athletes. A typical wearable device is the electrocardiogram sensor or the ECG sensor, and it is used to check the heart's rhythm and electrical activity. And continuous ECG monitoring can help identify an unusually fast or unusually slow heart rate, and therefore it is recommended for all patients with signs of acute heart failure. So if, let's say, you have some ECG monitoring patch on your chest, and you want the data to be displayed on your smartwatch. So you need a link between the two nodes on your body. So to be able to do that, there are many different ways that we can couple these together. We can use typical RF waves, so for example, we can use Bluetooth or Zigbee. We can use ultrasound waves, electric fields, magnetic fields, but we can also use electrical currents through the body, also known as galvanic coupling, which is a type of intrabody communications. Intrabody communications is a technique that uses the human body as a transmission medium for electrical signals to interconnect devices in various body area networks. Galvanic coupling is preferred over RF coupling because, as you can see in this graph, the propagation through the body is superior to propagation in air at frequencies between 0 and 30 megahertz. So at low frequencies, using IBC is much more efficient. And by using low frequencies, we consume less power. And number two, we do not radiate outside the body, so this is more secure. So what we propose is an end-to-end galvanic coupling intrabody communication system. On a very high level, what we're doing is that we are taking the ECG signal from the chest. We are passing this through our transceiver, through the transmit chain, feeding it to our transmit Ibc electrodes, then sending it from point A to point B on the body. Then we are retrieving the signal back into our receive chain, which consists of the analog front end and microcontroller, and then displaying this on the screen. So why is our work novel? Well, for several reasons. First, our system is compatible with the IEEE standard for IBC because we are using a carrier frequency of 21 megahertz. Not much transceivers do that. We are experimenting with VCH error correcting codes for IBC, which has never been done before. We are using our own optimal and flexible electrodes, so we're not using off-the-shelf components. And finally, our system is highly integrated because we're developing the whole thing from the beginning to the end. In addition to that, we're adding to the literature and in galvanic coupling, which is considered a much newer research thrust when compared to capacitive coupling, for example. So, as I said, our system consists of three main parts. The Ibc electrodes, which are flexible and optimized for intrabody communications. The analog front end, which consists of the amplification, filtering, digital analog and analog to digital conversion, and the digital back end, which consists of the modulation, encoding, and processing of the signals. So first, I will be talking about the Ibc electrodes. Now, electrodes are nothing new. They have been available for decades and even centuries for stimulation and reception purposes. But the problem here is that these same electrodes are now being used for intrabody communications without much thought. But electrodes for stimulations can be quite different from electrodes that we need for communication purposes. If we want to stimulate something, we typically use a circular electrode because we would like to have a uniform surface current density. But for intrabody communications, the situation is a bit different. We have two electrodes, and these are differentially excited. So there is coupling between the two electrodes, which we do not want, and a circular electrode may not be the best shape to use, for example. So what makes a good electrode for intrabody communication? Well, we can study the effect or the performance of this electrode by minimizing the reflection, maximizing the transmission, and also minimizing the specific absorption rate, which will allow us to minimize the losses and, of course, adhere to certain standards. So what are some electrode parameters that we can study? Well, there are many. We can study the effect of the electrode substrate thickness, the area, the electrode skin interface, the channel length L, the location on the body, the substrate material, the shape of the electrode, the inter-electrode distance D, the feeding configuration, transmitter's power level, output impedance. There are many, many different parameters that we can study and try to optimize. And to be able to do that, there are many different models, such as electric circuit models, electromagnetic models, and phantom models. But we choose to go for electromagnetic models because they provide the highest accuracy. And these are the two models that we used on HFSS, so the full body model and the multi-layer dielectric block model. And we previously, in the fall, presented our simulations that we have done. We studied the effect of all these parameters by simulation on our electrode, and we reached many different conclusions. For example, increasing the electrode area gives us a better performance. We also studied the effect of the transmit power and found a linear relationship between that and the specific absorption rate, and so on. But now we wanted to actually fabricate these electrodes and perform some experimental measurements. And for that, we found many different techniques. We could use inkjet printing on Captain polyamide, which is a flexible substrate. We could inkjet print on fabric, on paper. We can also use screen printing technique on fabrics, and we can also send our designs to a PCB manufacturer. But in the end, and due to time and financial constraints, we decided to go for a flexible copper foil sheet of 0.1 millimeter thickness, so it's still flexible. And we fabricated these electrodes. So we have 3 different shapes, and each shape has 3 different sizes, small, medium, and large. So for example, the small is 2.25 centimeters squared, which is the same for all the 3 shapes. So they're different shapes, but they have the same size. We also used a commercial disposable electrode as a reference electrode, and now we wanted to do our measurements. And it was clear from the literature that there was no unified technique for Ibc measurements. Each author used a different technique, ranging from using signal generators to oscilloscopes to VNAs to battery-powered transceivers and so on. And each of these setups provide a very different input impedance and requires different connections and so on. So in the end, we decided to go for the VNA measurement setup. Now, one thing to note here is that these electrodes that we have on the body are connected by regular wires, and they need to be connected differentially to our coaxial cable that is coming from the VNA. So 2 things to note here. First, we need to take the effect of these wires into our simulations because the VNA reference plane will be at the end of the coaxial cable, so we have done that. And number 2, we need to find a way to connect the coaxial cable to these wires. So to be able to do that, this connection, we found different alternatives, but in the end we used this type of pattern, which provides convenient connections, and we also constructed our own coaxial to a terminal block converter. Okay. Now, using the balun using this type of balun actually provides much more than this convenient connection. Using a balun first breaks the internal ground loop of the VNA, so it allows us to better mimic a real-life system, because in real life the transmit and receive will not be connected to the same system. They're completely independent. And number 2, if it is not a one-to-one balun, this provides an impedance transformation and also allows us to experiment further with different input impedances and see how this affects the electrode performance. So we took this balun and we tried to characterize it, and it was was found that the attenuation is acceptable on the frequency range of interest. Here I'm showing our experimental setup. So these are our electrodes. This is Johanna's hand, and this is a wristband. So the electrodes are placed under the wristband. This is wrist to arm measurements here, characterized in the VNA, and this is wrist to leg measurements. And then we performed more than 80 different individual measurements that took into account 9 different parameters: the shape, size, distance, length, and so on. So we had many different plots, but I will very briefly present some. So first, for example, here, this is the commercial electrode, and we simulated it without connecting it to the body. So we put them back to back like this to see the effect of the attenuation that is presented by the electrode itself. And you can see there's a high attenuation of around -50 to -40 dB. Next, we measured the effect of changing the wire length right here that connects the coaxial cable to the electrodes with and without a balun. We measured the different electrode shapes, also with and without the balun, for reflection and for transmission, different electrode sizes, different electrode distances, and finally different channel lengths. And in the end, I just want to say that we did not use a gel, although it was an option and we tried using it, because gels are not very suitable for long-term use. They cause skin irritation, signal degradation because the gel dries over time, and finally they're inconvenient because you need to prepare the gel and apply. So next I will hand it on to Christian, who will talk about the analog front.
Okay, thank you, Hani. So I will take over and discuss the analog front end, which includes amplification, filtering, DAC, and EECE. So as Hani first introduced, our transceiver is composed of 2 chains, the transmitter chain and the receiver chain. In the case of the transmitter chain, the ECG electrode sends an analog signal and sends it to the ECG module to process it. And we have then an analog output, which we need to pass to the ADC to convert from analog to digital, in order to pass it to the microcontroller and do some modulation and some encoding. And then we need to convert it again from digital to analog and do some filtering using the low-pass filter in order to transmit it via the transmission Ibc electrode. So during the transition, of course, there is some attenuation. And when the receiving Ibc electrode sends this analog signal, it needs it does some amplification, some filtering via the bandpass filter. Again, the signal is converted from analog to digital, passed to the microcontroller for demodulation and decoding, and then at this stage we can visualize it on a monitor. So here you can see the heart rate monitor front end that we use in our system. So as I said before, its output is analog, and so it is crucial to use an ADC after it. And to test it, we needed to have the raw analog output. So in order to do that, we supplied this module with 5 volts, and then we fed the signal to an oscilloscope to see the variations in the voltages. So as you can see in the oscilloscope screen, you can see the variation of voltages with a peak of 872 millivolts and minimum voltage of minus 520 millivolts. Okay, so in the transmitting chain, an ADC, an external ADC is not required, since the signal that is passed here is a very low frequency and of order of several hertz, and the sampling frequency of the ADC that is integrated into the microcontroller has a sampling rate of around 200 kilobits per second. So if we recall the sampling theorem, to avoid aliasing, the sample rate of the digitizer needs to be at least twice the highest frequency component in the signal being acquired. Therefore, we can conclude that an external ADC is not needed, since the sampling rate of the one integrated in the microcontroller is enough. So now concerning the DAC, we were aiming for a sampling frequency of 50 megasamples per second, however, which is approximately equal to 2.5 times the original frequency we had in mind, which was 21 megahertz. However, due to some shortage in components, we couldn't get our hands to the one we had in mind. So we had to order another one, which is the MAX 5853, which is a dual 10-bit 80 megasample per second current output band. So at this stage, designing a low-pass filter is crucial. The cutoff frequency has to be equal to fs over 2 or 80 megahertz over 2, where 80 is the sampling rate of the DAC that we have chosen. We designed, due to non-ideal roll-off, we designed a low-pass filter with a cutoff frequency of 30 megahertz, and the performance of this filter can be seen in this figure. The transmitting front end includes a DAC, a low-pass filter, and some biasing circuitry. And we can see here the values of the R and C components that we used in the PCB fabrication. So we designed the PCB in a way to allow testing and troubleshooting. So to test this PCB, we wrote a code on an Arduino microcontroller. And what this program does, it feeds to the DAC a different sequence of digital bits. And those bits are controlled by a potentiometer. And those bits, they range from a sequence of all zeros to a sequence of all ones. Okay, so here for the receiving chain now, we wanted to replicate the receiving analog front end through behavioral model simulation using PSpice. So our input is a sine wave of 1 volt amplitude and frequency 21 megahertz. We gave it some channel loss of around 0.03 and then amplified it by 4.84 times. Why is it 4.84? Because if you convert it back to decibel, it's 13.7 dB, which is the gain of the amplifier we ordered for our system and that we use for our system. So now this amplified analog signal goes into this ADC 12 rate, which is a generic ADC used in PSpice. So it converts the analog signal to digital to 12-bit, and then we map each bit to a DAC in order to see if our input signal was reconstructed at the output. So here we did a total of 2 tests, and there were the same parameters, but the only thing we changed was the clock speed. So for example, for a clock speed of 500 megasamples per second, we can see here in red, we have a signal that resembles the one that resembles input, with a little bit of attenuation which was expected, and some phase shift, and it is really smooth compared to, it resembles the input as it is smooth. And for the second case, with a clock speed of 50 megasamples per second, if we zoom in on this graph, we can see some clipping on the peaks and the troughs, and the same thing, the same phase shift. But for the sake of our project, we believe that the 50 megasamples per second was enough as a sampling rate for our ADC. Now I will pass to Johanna.
So now to talk about the digital backend. This includes 3 main components. First, modulation, encoding, and its backbone, the processing. So processing is the main part of the system, and we need to decide on whether to continue with our original thought of using an FPGA or to use a microcontroller. Due to a lot of constraints and mainly times and complexity and development and a lot of issues, we decided to use a microcontroller. Now, on this microcontroller, we needed to implement encoding and modulation. And from the fall, we decided to use BCH error correction, and we still needed to decide on what modulation technique to use. So the BCH encoding that we decided to use is the 6351 BCH encoding, which adds around a redundancy of 20%, and this is capable of correcting up to 2 bits of error. Now, we needed to test this with the 3 main modulation schemes, which are all phase shift keying. And in this case, we use BPSK, QPSK, and EECE. So this is the system we did in Simulink to be able to test them out. As we can see, the BCH encoder takes 51 bits and outputs 63 bits as a frame. And there's only one difference, is that QPSK requires a multiple of 2. So we have to use a paddle to add a 0 at the end in order to feed it 64 bits, and then we remove it into RX. Now, using this simulation, we were able to get the following MATLAB plot. by varying the SNR of the white Gaussian channel. Now, obviously, it's very clear which one is the winner, and it is the one that has the best fit line drawn, which is BCH and BPSK. Obviously, BCH improves the PER values, and BPSK is the one that performs the best. Now, for the signal processor, as I said, the first choice was the FPGA, and due to my constraints and a lot of other reasons, we weren't able to use it. So we needed an alternative. And the alternative would have been, per Dr. Mazen Saleh's recommendation, ESP32. This was a board that's available at the AV readily and has a lot of features to compensate for the lack of the FPGA. Now, I said that the lack of I/O in the FPGA was a disadvantage. However, it's unlikely to use two FPGAs, one for the transmit system and one for the RX system. So in this case, you can use two ESP32s without worrying about that because they're relatively cheap and small. It has a fast processor and it's around 240 megahertz. It's easier to code, obviously, because we'll be using C instead of Vivado and Verilog, which is a whole thing by itself. And we'll be using the Arduino IDE, which is very simple. And in this case, it has the advantage of having built-in EECE and a built-in DAC. And both of these are very essential for our troubleshooting in order to know which part of the system isn't working. As I said, we're testing the whole system and we need to be able to test it in parts. So this is the system I showed. First, we decided to test this part. So this code is designed to take the ECG reading from a specific pin and then write it using the built-in DAC. There's no real processing here, but we wanted to see if it was able to write the ECG signal properly. We tested this on Christian. And if you can see in the back, we have reconstituted the ECG signal. It was a bit noisy, but this was mainly due to the ECG cables, which was fixated on. So in this case, we tried sending a 50 kilohertz square wave through the body, again, Christian, from these electrodes to these. And as we can see, the square wave wasn't perfect, but it was fine, more or less. And here we just added the mode to it. Now, as we can see, the transmitted ECG signal is very similar to the one received. However, we have some attenuation, and it is obvious due to the size of the electrodes, the distance, a lot of other things. Now, for this testing, we used the medium circle electrodes that Hani designed, and we didn't bother testing with other ones. We just wanted to see how the system works. So in this case, the TX microcontroller gets the signal from the ECG, it passes it on to the DAC, then it goes back to the RX microcontroller through the body, and then it's displayed on the oscilloscope. So obviously the transmitted ECG signal is directly the output of the TX microcontroller, and the received one is the output of the RX microcontroller. Now, future work is very essential for this project because, as Hani mentioned before, it's very research related. So, as for the electrodes, more rigorous testing is needed because Hani's simulations weren't very consistent with the actual theoretical simulations. So we need more testing about the sizes, the shapes, the distances, the parts of the body. Then we need to actually increase the frequency to 21 megahertz. The reason why we didn't use 21 megahertz in our simulation is because one of two things would have happened. Either we would have to buffer the signal enough to transform the 2 hertz signal into 21 megahertz, which would not be in real time, which would be very delayed, or we would have to send in real time an empty signal that has very few information. If we were to use 21 megahertz, we'd need a higher clock speed, and this would require the use of an FPGA with a dedicated crystal oscillator, and it would facilitate the implementation of modulation and error correction. Also for modulation, we could use specifically Manchester coding, which would have in EECE, so it's self-synchronizing for the clock, so it would also make the demodulation part easy. So this project as well is very interdisciplinary. It combines almost every single class we've ever come across, and it has everything. So just wanted to point that out. And this is our poster. So basically, this is the result of whatever future work we have in mind. In this sense, we will have standard compatibility, BCH error correction, the optimal flexible electrodes, and system integration, obviously. We can see some snippets of the electrode design, the analog front end, and obviously the digital back end that encompasses BPSK modulation as well as BCH error correction. And this is the working system with the that on the PCB that time fabricated, as well as the transmitted and the received state. Also, we'd like to thank Dr. Joseph, Dr. Wael Lagrange, as well as Dr. Fuda and Dr. Kubrahi from UCLI who helped us and guided us through the project. Thank you.